Welcome to the second video actually on the feedback pair transistor. In the previous video, we had studied about the feedback pair transistor DC analysis. Continuing with that, here we will be doing the analysis of feedback pair transistor. We call it as an AC operation analysis, AC analysis or an AC operation. Correct? So here what we are doing, earlier for DC analysis we removed all the AC components. Now for doing a AC analysis here, I'll be removing all the possible DC components. So let us do the AC analysis of a feedback pair transistor. To do an AC analysis, we need to know the basics of writing a small signal model. I have already explained in detail how do we write a small signal model in the previous videos. Please refer to it. Here I am directly assuming that we already know AC signal analysis. I am directly writing a small signal model. Okay. So let's write a circuit for it. So just first let us have a proper look here. What do we have? We have Vin applied to the base of first transistor, correct? So here this is base, this is emitter, and this is a collector terminal for the first transistor. Similarly for the second, this is base, this is collector, and this is a emitter terminal, correct? So where there is a junction where this current is bifurcating. One path it is choosing to the emitter of first transistor. Second, it is choosing the path to the collector of the second transistor. So having all these in mind, I am developing a small signal model. Now let us write a transistor first. We know for a transistor, we have small internal resistance and a current source, correct? So from base to emitter, I have small internal resistance. So basically we were calling it as Ri. I am now calling it as Ri1. So this is beta 1, E1 and collector 1. So this is my first transistor. So the gain is IB1 and beta 1. Similarly, I have my second transistor of same type. So this is my base, collector, emitter. So here the resistance I am calling it as Ri2. Current source we basically call it as beta 2, IB2. Correct? Now this is a transistor model, transistor equivalent. For this, let us write the entire rest of the circuit. So to the base, I am applying input voltage. From there, RB was supposed to be connected to the ground. Correct? So this is my applied input. This applied input gives rise to current, input current I1. There is a current flowing through base of my transistor. So that current will be IB1. Correct. Now collector and second transistor are interconnected base. Correct? See here. This part. So I have just connected. So this emitter is directly grounded. Looking here. Correct? Next, the output of my second transistor will be acting as an input to my from there I am connecting RC where the current IC flows. Here I am measuring V out. So from V out I am having the current I out. So putting down the current here, current direction here. So IB1 through first transistor. Similarly IB2 from my second transistor. Now this is the first level of representation of small signal model for a feedback pair transistor. Having written this, so now this looks little uneasy because we have a different layers here. So I can simplify this furthermore. So after rearranging, simplification in this is just a rearrangement of this particular circuit. Let's do that. So for rearranging the circuit, I am writing with RB. To one end of RB, I am connecting input voltage. To other end of RB, I am connecting ground. In other sense, I am connecting VI across RB positive and negative terminal here. From that path, there is a small resistance RI1 through which a current IB1 flows. There I have a current source. That current source is beta 1 IB1. So here again I have an internal resistance Ri2 through which current IB2 flows. Correct? Entirely parallel to this, I have one more current source, but this current source is opposite in nature, correct? So I am writing a downward arrow. So I have beta 2 IB2 here. What is left? We have the resistance RC left here, across which V out is measured. So this is a simplified small signal model. The same way, let us now derive different parameters of the circuit, that is AV, AI, Zin and Z out. The procedure for derivation is almost same. So I am quickly doing it. It is similar to Darlington circuit, which we have already discussed. So first step, I am applying a KVL to which loop? To the outer loop of the circuit. So come to this. What is the outer loop? VI through RI through RC back to VI. This is the outer loop of the circuit. So writing the KVL for it. VI minus current was IB1, RI1. Next, current was IC, RC is equal to 0. Why am I writing plus? You can see the direction of the current opposite. Correct? And we already know from a transistor equation, IC is equal to first emitter current and second, see here, first emitter current and second collector current. That's what we have written. And in the DC analysis also, in the previous video, we have seen that IC2 is equal to beta 2 IB2 and IE1 is beta 1 IB1. So what will be the total current here? Substitute this. Total current IC will be equal to what? Beta 2 IB2 plus this term beta 1 IB1. So this is the total current IC. So here if you see, we have seen it already. IB2 is the output of my first transistor. IB1 is the input to the first transistor. So amplified, correct? So always we can assume that the output current is greater than the input here because current is getting amplified. So we can negotiate it here that assume IB2 is always greater than IB1. Hence, IC can be solely written in terms of IB2 into beta 2. Correct? And if you consider after cascading, IC can be equal to beta 1, beta 2, IB1. Putting all this substitution, the circuit input impedance and output impedance has to be calculated. So, writing on the small signal model here, I am representing the impedances here. If I see from here, I will be getting Zn. At the same time, if I see from here, I will be getting Zb. So, if you see from here, Zb is the same way for Darlington, we had already written. Okay, let us take the KVL again, is equal to IB1 first resistance, IB1 into beta 1, beta 2, RC. What is this? This is from your total. So V by I, take IEB common. What is left? RI1 plus beta 1, beta 2, RC. From Ohm's law, after rearranging, I can say ZB is equal to this term, right? RI1 plus beta 1, beta 2 into RC. So ZB is parallel to resistance RB. So Zn is equal to ZB parallel to base resistance RB. This is input impedance. Correct. Now let us do the current gain. Current gain. What is the representation of current gain? E of I. So current gain, as the name itself is telling, it is a gain term. A of I is equal to output. What is output? I0. What is input? I1. So I am just multiplying and dividing by the same term and rearranging. I am multiplying and dividing by IB1 by I of I. Here this term is mathematically similar to this. Correct? Now from the circuit, if you see, coming to the circuit here, what is output voltage? Output voltage is IC, correct? But in the opposite direction, negative. So I can write, we know that from the circuit, is it not? I0 is equal to minus IC, and minus IC by IB1 will in that case becomes beta 1 into beta 2. Now coming to the circuit, I am rewriting it here. I0 is equal to minus IC by IB1 is equal to beta 1 into beta 2. I am just rewriting it here. Next, coming to a KCL, I am applying KCL to the base node. Okay, that is which base? B1. If I am applying KCL to base 1 node, what will I get? Input current is equal to two bifurcations there. One is to the base, the other one is to the resistance RB. I am assuming it is flowing into the resistance RB. Correct? So we know input voltage is parallel. So IB1 ZB, which indicates I1 can be this one from this equation, can be rewritten as IB1. I am taking common here, 1 plus ZB by RB. Correct. I am taking term, transferring this term to the denominator. IB1 is equal to 1 plus ZB by RB. Combining these two terms now, A of I, here we had written the formula, right? I am substituting it. Here, combining both the terms, I have beta 1, beta 2 into RB. I am taking an LCM for this, divided by RB plus ZB. This is the equation for current gain of the Darlington feedback pair transistor. So we have seen the last point, last term that is left with voltage gain, AV, voltage gain, AV. To calculate an voltage gain, we have V out is equal to beta 1, beta 2, IB1 into RC. Because IC we know, IC we have written it as beta 1, beta 2 into IB, IC into RC is the output voltage. Now in the initial we had written minus IB1 RI1 minus V out is equal to 0. This is from KVL to the outer loop. Initially we started with this. So I am substituting it here. VI minus V out divided by RI1 rearrangement. So let us substitute what is IB1 into this equation. V out is equal to beta 1, beta 2, RC, VI divided by RI1 minus, what is it? Beta 1, beta 2, RC, V out, correct? Divided by RI1. I am just splitting the terms, correct? Let us take the common terms there. V out into 1 plus beta 1, beta 2 into RC divided by RI1 is equal to VI beta 1, beta 2, RC divided by RI1. This is a rearrangement from this equation. All V out terms on one side, all input terms on one side. Let us exchange the terms. V out by V in, that is equal to beta 1, beta 2 into RC whole divided by RI1 plus beta 1, beta 2 into RC, which is nothing but the voltage gain. Hope everybody have understood this particular derivation, AC analysis on feedback pair transistor. If there are any queries or doubt with respect to this, please let me know and I shall solve it as soon as possible. So the base for this is writing this particular simplified small signal model. Thank you for watching the video. You can always write back to me for any queries. Thank you so much.